Good morning, everyone. I'm Siddharth, and I'll be moderating this session. So, I welcome all of you to another exciting day at the 24th Annual ARC Industry Leadership Forum, India 2026. Yesterday, we had set a remarkably high bar with enriching discussions spanning industrial AI and its impact on sustainability and logistics, smart manufacturing and digital transformation, MES and refinery operations, asset reliability, and last but not the least, autonomous operations. So today we are carrying that incredible momentum forward, beginning with a focused session on industrial AI use cases in manufacturing. We have an outstanding panel lined up to guide us through this. We will kickstart this session with a presentation on digital AI powering industrial futures with DS Latha, Senior General Manager and Discipline Head at TCE, who will be later on joined in the panel discussion by Subramania Edamana, General Manager of Mechanical at TCE. Following that, Mr. Kande Ramesh, Senior Vice President of the Global Capability Center at EET Fuels, will lead a detailed discussion on remote machinery surveillance using wireless sensors in global refinery. Finally, we will conclude the session with a presentation on scaling manufacturing with industrial data ops and agentic AI delivered by Mr. Vinod Ninan, Head of Product and Portfolio Management for ABB Automation. Please join me in welcoming our first speaker for the day. Ma'am, the stage is all yours.
Thank you, Karthik. A very good morning to all of you. I'm from TCE. As most of you are aware, TCE is a 64 plus year experienced engineering consultancy organization providing concept to commissioning services for industrial plants in the field of power, hydrocarbon, chemicals, mining and metallurgy, and lately digital and advanced services. We have engineered some of the finest systems in the industry, ranging from the oldest 150 megawatt thermal power station in 1956, radio telescope in the 1960, which are relevant even today. Asia's largest water treatment plant, India's tallest chimney, Ayodhya Ram Temple with a design life of 1000 years, and we have partnered with the world's largest fusion reactor, ITO France, and India's space program, ISRO GSLV launch. We are also involved in Mumbai High Speed Rail, world's largest green ammonia plant, India's first hydrogen refueling station at Ladakh, the anti-drone systems in Mumbai, and India's first semiconductor plant and the solar PV glass plant. We are also involved in design of city command control centers, etc. Uh, Lately, we have developed and utilized digitization and yeah, and AI tools too, few of which are a part of my presentation. AI supports decision making across the entire project lifecycle, from feasibility reports to operations, providing unified project insights by integrating comprehensively the procurement, engineering, and construction data, creating a change impact and supporting decision making. AI in planning and forecasting enhances the cost and schedule predictions by analyzing historical data and dynamic scheduling. AI driven design optimization provides engineers with multiple design options quickly for evaluation and minimizes reworks. An example could be a building design wherein once the design is made, if a person wants to add or delete a floor, they could, with the click of a button, they could generate a new drawing without or with additional floor and estimated new bill of quantities. Once a prototype is made, same criteria could be applied for similar designs. In construction, safety is of paramount importance. AI strengthens safety leadership by identifying unsafe patterns and risks proactively. AI is also used in commissioning and maintenance, applied in the form of digital twins, predictive maintenance, and real time optimization. Most organizations are implementing digitization and AI tools as a part of the routine task to improve efficiency and save time. Few levels of this transformation include level 1, wherein there is paper to digital data migration, cloud storage and infrastructure implementation, and use of digitized core productivity tools like BIM, drones, image processing, and digital schedules. Level 2 integrates these core productivity tools, which are in different operational silos, by interconnecting cross functional platforms like Revit, Navisworks, and so on, Tekla, etc., and automation and automates seamlessly, generally using unified data lakes or common data environments. Level 3 uses predictive analytics and optimization tools to improve delivery. Level 4 achieves project intelligence and employs AI tools like digital twins. As a part of plant digitization, we have executed digitization of an existing plant using 3D laser scanning. Here, the plant area are defined by segregation into multiple zones, and multiple scans are taken from different angles across these zones. Scanned data of multiple zones are stitched together to collate into cluster cloud points from which form the basis of input for the 3D models. We also have the bubble point views, which are static screens used to obtain more clarity of equipment and the arrangements. The developed 3D models are further authenticated by at site and developed into as-built documents, which can be further developed into BIM model, superimposing COBie data and scheduling data for optimum plant maintenance. We also have hazardous area laser scanners, which could be used for hazardous area laser scanning. And then, as a part of plant digitization, we have also used drones. Drones equipped with high resolution cameras, thermal cameras, and LiDAR capture images of or videos of assets in inaccessible areas or in hazardous areas and store data digitally. This is followed by human inspection, which who examine the footages to identify defects in general. However, we have AI powered drone inspection, which is a next generation approach wherein drone collected data is analyzed using AI models which automatically detects defects and anomalies. We have used this in bunker inspection for steel plants and to identify structural defects. Other use cases include pipeline leak detection, boiler and turbine inspections, structural inspection, panel defect detection in case of solar plants. Coming to digitalization, we have building information modeling. BIM model development begins with a preliminary design, commonly referred to as a 30% model, containing basic geometry, layouts, space planning, etc. Further, this model is progressively developed through 60 to 90% design stages with increasing levels of detail and accuracy. The next step is a model coordination and collaboration. Model coordination involves establishing a common project coordination system and integrates models from different disciplines into a single federated BIM model, like from architecture, civil, piping, plumbing, HVAC, electrical, and so on. This combined model is further used for clash detection and resolution, identifying and eliminating the design conflicts before the construction begins. BIM can also be effectively integrated with site operations using iPads, iPhones, or Android devices. These site teams can access the latest BIM models in real time review construction details directly on site, capture photographs, and attach them to the model as comments for further engineering updations. This can also be used to report progress and update construction status through cloud connected platforms. The idea of this unified BIM model is that it improves communication between design, construction, and project management and ensures that the same data is available with all the stakeholders. Then we have the 4D simulation in BIM model, wherein planning and scheduling software like Primavera or MS projects are interlinked. So we have a 4D model of BIM, which is a combination of 3D plus time data, which is used for digital project monitoring. We also have the mixed reality technologies like the Microsoft HoloLens, which enhances project visualization by overlaying the BIM models onto the physical construction site. We can enrich the BIM model by attaching COBie data, which are basically the equipment data sheets, equipment specifications, O&M manuals, warranty information, and maintenance requirements, which can be accessed by the site personnel at any point of time using digital tracking. We also have the digital twin at the top of this model, which are digital replicas of physical assets, wherein simulation can be carried out throughout the project lifecycle as well as after plant commissioning to understand the project dynamics, ensuring corrective actions to achieve optimum plant efficiency and operation. Yeah, generally BIM models are developed as levels of development. LOD 100 is a basic 2D model followed by LOD 200, 300, which is a 3D model. 350 is a construction ready model uh, involving class detection and resolution. And we have LOD 400 for generation of bill of quantities for fabrication and assembly. And LOD 500 is the highest level, which is a final as built model. This is a typical BIM model review cycle. As you can see, we have the BIM model generation. Then the next step is a 2D to 3D conversion. Then we have class report generation and coordination review. The virtual model review with all the engineers in the organization, and then we could send the documents to client or in-house between the different departments. The final review and submission takes place and the document is ready for construction. This is a typical BIM milestone captured for a water treatment plant. Here I forgot to tell about one thing. The first step for any BIM implementation is the development of a BP. BP in any model includes development of a it's like a basic specification which includes all the list of softwares to be used for the platform, the various tagging philosophies, the type of equipments to be developed, etc. And then we have the Revit family creation, conversion of from 2D to 3D, clash and coordination, addition of COBie data, and the final BIM model. This is the picture of a desal plant. Here you can see the 2D model which was generated initially. Then we have the different 3D models developed by different disciplines. And then these are consolidated into a final 3D model which is shown at the top of the page. You can see the RO shed which is completed, air blower, the filters, clarified water storage tanks, and the pretreatment unit in complete form. We have implemented BIM for Mumbai Ahmedabad bullet train project. Here, this is a very interesting project with a linear structure of approximately 503 kilometers. And you can see the various pictures which indicate the extent of work involved. Though this is a linear structure, we have the platforms at different levels, as you can see in the last picture here. Clash detection, safety analysis, etc. were done on this model. Then we have also done integration of BIM in 4 gigawatt solar PV cell and module manufacturing plant. For this, we got the Autodesk Imagine Award, and this was implemented in a period of 6 months with a detailing level of LOD 40 and generated around 300 GFC drawings, which was a feat in itself. We also have implemented the automated advanced process control in thermal power plants. APC solution is a promising digital solution which aids digitalization, improves plant performance, and enables flexible operation. It uses model predictive control and AI-based intelligent algorithms that continuously learn from process variations and drive the process to optimum point. APC enables real time optimization, improves plant flexibility, and reduces operational costs while ensuring environmental compliance. Various steps involved include digital data analysis, flexibility assessment, the base layer control improvement, combustion tuning, APC deployment, and asset integrity checks. TCE has a strong domain expertise in thermal power plants, proven implementation capability for APC solutions, and we also have expertise in integration with major DCS platforms. So, these are the features which are implemented in APC. APC is deployed for heat rate improvement, temperature control, the superheater and reheater, reduction in the SH and RH spray, improved combustion and reduction in emission, reduction of excess oxygen, and better pressure control and stability during ramping for increased operator comfort, which finally led to a carbon footprint reduction. We also have the dynamic line loading solution, which was implemented for 400 kV transmission line. DLL is one of the latest technologies which is used for transmission line. Here we have the components of the system include DLL sensors, sensor data servers, communication platforms, and then a plethora of softwares and hardware. Dynamic line loading is an advanced smart grid technology which enables management of stable power flow in overhead transmission lines based on local weather conditions, seasonal changes, and daily load variations. It allows for real time adjustments to the capacity of the overhead transmission line in response to fluctuating climatic conditions. And then some of the benefits of implementing the dynamic line loading solution include a reduced risk of overheating the lines and preventing line failures. It also provides for better grid management and reduced greenhouse gas emissions. Decreased or deferred capital costs through improved utilization of existing assets. For example, if we have a transmission line already and we using these DLL sensors, we could check whether we can add additional power to be transmitted to the same line, preventing further installation and reducing the installation costs of the new lines. As a part of artificial intelligence, we have developed an in-house tool, which is a digital twin for aluminum sorting plant. This is developed using NVIDIA Omniverse platform, and salient features of this digital twin include real-time synchronization, simulation capability, and 3D visualization. And the benefits include improved plant efficiency and reduced downtime, cost optimization, better planning and decision making, enhanced safety. And use cases are in this case are conveyor belt monitoring, material sorting and optimization, downtime prediction, safety monitoring, operational planning and energy optimization. We have also developed an AI powered tool for construction site safety monitoring, which is done using advanced video analytics and NVIDIA's accelerated computing ecosystem. This system enables a wide range of advanced functionalities like real time safety monitoring and multi object tracking, PP compliance detection, zone based monitoring like crane exclusion zones, restricted area violation detection, behavioral analysis, and multi object tracking. Benefits include improved worker safety and reduced accident rates, faster response time to hazardous situations, and enhanced compliance with safety regulations and standards. We have also developed an AI tool for HSR Surat Station, which is a digital twin again. It is a high fidelity real time digital twin with a strong emphasis on operational readiness, passenger flow optimization, and safety validation. Salient features of this tool include 3D station visualization, crowd analytics, integrated monitoring, and unified view of all station systems and assets. The benefits of this AI tool include improved passenger safety and crowd management, optimized resource utilization and operator efficiency, enhanced decision making for station authorities. These are some of the tools which we have developed long back, and I would like to just give you a glimpse of this. This tool is basically used for quality control and defect detection. AI technologies, including computer vision, pattern recognition, CNN, and YOLO V8, are employed for this. This tool identifies fractures in this tool helps in identification of fractures and accurate injuries like cracks along with dimension, location and heat map. It also detects pores along with this is the drawing. This tool also identifies pores along with the dimensions to check material integrity, basically strength and quality assessment in case of concrete. This can also be used for steel applications wherein it detects cracks and frizz along with the location and dimension. We also have predictive maintenance tool for rotary equipment using AI techniques for pumps and motors. We also have a Gen AI operational enhancement tool similar to a ChatGPT, which is used for scoring and retrieving our in-house knowledge bank. We have an AI driven PNID automation tool which converts PDF to AutoCAD PNID. We have the AI SLD, the intelligent SLD generation tool, which is done very nicely. Here we need to enter very few data like voltage, power frequency, and important electrical parameters like feeder ratings and whether it's a single bus, dual, or triple bus configuration. The output will be an SLD with incoming and outgoing feeders along with metering and protection, which is the first of its kind in India. And we also have a plethora of digital point solutions for thermal plants and renewable plants, uh, which is shown in the slide. To conclude, AI adoption is faced with pilots, validation, and scale up, ensuring transparency, risk mitigation, and institutional learning. Decision making, however, remains with humans and is hierarchical as on date. and AI provides advisory insights only. However, I'm very optimistic that in future we could have AI tools to design industrial plants and systems by providing a range of variable input parameters and the expected product complying to the regulatory requirements, providing more time for mankind to engineer a better tomorrow, which is the motto of our organization. Thank you.